Okay, today we're going to take a look at the second part in the tube power supply series. Going to be having a look at the plate supply. That's this unit at the bottom here. I'm just first of all showing everything together with the experiment. So this unit we looked at previously. This is the heater grid and screen unit. It's got the quad 811A tube board on top. And this is how they're intended to be arranged. So we have the heater grid screen supply, we have the plate supply at the bottom here, that's all mounted on a plastic trolley, and then we have this region here for other units. So that might be matching unit, might be an input-output unit, something of that form. So we're going to be looking at detail in this plate supply. And we'll be having a look, and also be having a look inside, explaining how it works, and it's intended to drive the type of experiments that I show on my website. So here we have two cylindrical coils facing each other. It's a typical induction generator type experiment. Eric Dollard has obviously originally did the cosmic induction generator type experiments, plasma type experiments. These are very similar to that type of experiment. Also Tesla's radiant energy and matter and transference of electric power are all very suitable for this kind of tube supply. The plate supply is very flexible. It's designed to run from a very wide range of voltages and currents, and it can drive anything from the 811A all the way up to something like a medium power 5C22 thyrotron tube. So it's a very important addition to the laboratory experimental apparatus. It is quite sophisticated and has a whole different set of circuits in it. Obviously there's the high voltage transformers, there's a high voltage bridge rectifier, there's also a level shifter or a doubler in there, and there's also a high voltage discharge unit to allow you to discharge external capacitors, plus all of the necessary power control and safety features. So altogether quite an advanced supply. Okay, let me just, first of all I'm going to remove this unit off of the top. I'll put that aside, down on the bench, like so. And then I'm going to bring this in closer to the camera so we can take a look. Just get the camera on this unit and get it zoomed in. Okay, so the core of this unit is basically the high voltage transformers. It uses 3 industrial microwave oven transformers, so each of those is a 1.8 kVA transformer. So if I actually start from the back and we look at, I'll just check that's in view of the camera. About there. Okay, so this is our mains input, output and control board. This is the high tension output. It's made on a nylon board. Obviously there can be quite high potentials in there. This plate supply, if you were using all 3 transformers in series and you were using the doubler or the level shifter, as it should probably be called, then open circuit with all that going flat out, you'd be up to 18 kilovolts. So obviously all the necessary precautions need to be taken care of. If you're running all 3 transformers in parallel without the doubler, then you down to somewhere around about 2 kilovolts at about 2.5 amps. So The nominal rating of this is all the way from 2 kilovolts at 2.5 amps up to around about 15 kilovolts at 200 milliamps, by various arrangements of the transformers and using the various internal systems like the level shifter. There's also a high voltage bridge rectifier in there as well. So very flexible, very good for driving the range of tubes that I've shown and illustrated on the website, and also other tubes as well. We'll at some time in the future be covering the Thyrotron board with the 5C22s, and obviously looking at the experiments that go with that. So if we go back to this is where power initially comes in. So we've got two line inputs. I mean, this is nominally, if you were to run this flat out, essentially you could say it's a 5 kilowatt plate supply. So for two 833Cs, that's a tube board that I've already showed. You are say at 4 kilovolts, you running the plate, you can, and to the right load, push about 3.5 kilowatts out of those tubes, two tubes in parallel. This plate supply is capable of supplying that power. So nominally up to 5 kilowatts, 5 kilowatt plate supply. So the power board itself, we have dual line in. So nominally at maximum power it will run at about 30 to 40 amps. You've also got to take into account the power factor from the transformers. You also have two line out. So in other words, that's useful. For example, that will take a connection out of there, and that will connect to the input of the heater grid and screen unit, and also another spare one for another unit. I always arrange this so that two units could be run side by side, whether it's a twin heater grid screen because you're using a two-stage, or more usually you've got some kind of matching unit that goes here, either input or output from the tubes, depending on what kind of modes you're running your experiment in. There is also an output here for external power meter, and that's also how that is controlled, is how it's routed. It can either be routed internally, or we can route power monitoring out through this external connector to a Yokogawa WT200 or so. Power meter is very good. I use them typically for this kind of experiments, and that allows us to set it. So if we're not using external power meter, then we just set it to internal. That's off. So in other words, you will not end up with any power out of the front panel. So that's internal, nothing connected there. There is a power meter arranged on the front, and I'll come back to that. Then we have our primary earth connection. So this end is line earth. This is the transformer earth, or basically what, if you select the jumper options, what can actually be connected to the core of the transformers. If we remove that, we essentially float the transformers. So we're not connecting the transformer to line earth. That could be particularly important, for example, if we are running below, depends where the reference is, we're running 3 transformers in series, and we've got the bottom transformer pushing negative, while the other transformers are 2 series above it are pushing positive. Then, for example, we would want to disconnect the transformer earth from the line earth. Okay, I'll come back to the output panel once we've gone through the various other stages. So from the power coming in and the main supply, let me turn it around to the side, we move on to the power control board. So this is now on this side. So in effect, power comes in here, passes along this board, and then comes out of the front panel. So it's a straightforward and simple design. Okay, so first of all, the power coming off the back comes to these various switches. So you have the low voltage switch that basically just switches on an internal 15 volt 3 amp supply, so it provides the low voltage required for things like the fans and switching relays and those kinds of things. That also powers a DC to DC converter, which also gives you 24 volts. So you get 24 volts and 15 volts internally. The 24 volts is very good for the vacuum tube relays. So I use some vacuum relays in here. I'll come on to those in more detail. The B1B is normally a 3 kilovolt, 10 amp vacuum relay, and is very good in the measuring and the discharge circuits. So that's a low voltage. It's obviously got a fuse associated with it. Then we've got a 32 amp B32 MCB there, which is the main supply to the transformers. Obviously the indicators as well to show that the supplies are on for both the low side and the high side. Behind here then you have an SCR, so power control internally is accomplished by an SCR. The SCR sits behind here, the panel, and then the low voltage power supplies here. Two fans drawing in, and they can both be switched. They go behind the transformers, and they provide laminar airflow across the power supply and out through the large vent on this side. Particularly useful when you're working for sustained periods of time or at relatively high powers. Okay, so from here the power's come across to this now line selection switch. So here we're going to select where we can actually take mains power from. So at the moment it's off. So in other words, no power will be provided to the front panel. This is particularly useful in operation when you actually want to move the system to no power or turn it all off in one go. The switch there will turn off all control to the transformers. Now we've got two other settings. So off there, that is the SCR. So the SCR is the internal power controller and is controllable by the controls on the front and also from the remote control. So the back to 0, if you put it to position 2, which is external, you can actually then feed power in via these terminals. So they are connected together, so there's either a line input terminal or you can use the high voltage 4mm high voltage connectors as well. So this allows something, for example, like a variac to be connected or some other type of power control. So taking here, you are basically ignoring all the power for the transformers that comes through here and selecting an external supply. And that's particularly useful when, for example, you want to do an experiment where you need to use a variac or something like that. Then you can easily get access, and that then feeds the power through to the control system in exactly the same way as it would come through from the SCR. Normally I'm using it in SCR, which is its internal settings, and then I can control it by the front panel. So then we come on to the front panel. Let's just bring that round, have a look, make sure it's in on the camera. Okay, I'll turn it on. So this panel here is basically control for the transformers. So it's everything to do with the free transformers. So power that was selected comes round through here, and we have 2 meters. We have a complete power unit here. This is one of those power units that samples the voltage, and it has a current transformer of which either the live or the neutral passes through that current transformer, and then it can calculate a lot of useful parameters like voltage, the power, consumed power, the amps, the current being consumed, and also showing the power factor, and also the frequency of the supply and stuff like that. So very useful output, gives you all in one summary. I also like to have an analog indication because Sometimes when you're working with Tesla coils or with high ambient electric and magnetic fields, this kind of digital equipment doesn't necessarily operate correctly. So I always like to, at the bottom line, have analog instruments as part of the supply, because even if all the power goes, for example, those analog instruments are still going to work, and they're still going to show you what's going on in the supply. For example, particularly on the output, if you've got a large capacitor on there and it's charged up, that's going to show an output, and if suddenly your power goes for whatever reason, the circuit breaker trips or something, that is still going to show you the charge on that capacitor, and that can be considerable. I mean, with this kind of supply, you can effectively be charging up very, very large capacitors to very high potentials. I mean, with 3 of these, let me show an example of the kind of capacitors that might be used. So let me just make sure that's, you can see that in the camera. Okay, so that's the other type of capacitor that I'm using as well. So this is a 60 microfarad 4 kilovolt capacitor. You put 3 of those in series, and essentially you've got a 20 microfarad 12 kilovolt capacitor. That is considerable amount of energy, a very considerable amount of energy. That's why you also need a discharge unit. If your valve stops, or your experimental work stops for some reason, the valve stops oscillating, that capacitor can be that capacitor bank can be left with an enormous amount of energy on it. And before you can get anywhere into that circuit or make modifications or try something else out, you need to safely discharge that capacitor. And that's what the internal discharge circuit is all about. This is a pulse capacitor. That's a 25 nanofarad, 25 kilovolts, yes, 25 kilovolts, 25 nanofarad pulse capacitor. Extremely good for the Tesla coil tank. It can be obviously combined with others depending on the tank size, both for a arc discharge power supply or as a part of the tank circuit in a vacuum tube unit, which is how I use it. I will be showing in some of the experiments. This obviously doesn't have the same issues with the discharge, but nonetheless still useful to have that facility. Pop these back over. Okay, so if we go back to the front panel, I might zoom in on that so we can see it more clearly. Let me just... Okay, yeah. So going back, this then is the control for the transformers. We've covered the power controller. We can see the amount of current, AC current, being consumed. That's a 30 amp meter, and that's essentially RMS. So it's basically real consumed current. And the control now. So we have control for the SCR. We can choose whether or not the control from the SCR is internal or external by this lock switch. Now there's a remote control socket. I like to work usually by the experiment or the distance from the experiment if it involves very high tensions. So having a remote control, and that remote control for this system allows you to do 2 things. It allows you to turn on and off the output. It allows you, and that's by essentially controlling the SCR. It allows you to adjust the SCR with a potentiometer, and it also allows you to turn on and off the discharge circuit. So in other words, you can fully operate the internal settings once it's configured, however you want to, and at a distance. So here are the switches for the 3 transformers, T1, T2 and T3. They are basically a 3-position toggle switch, so centre off, so man they are all off. They can be put one way or the other way, with the centre being off. So in one way they connect live and neutral to the transformer. In the other way they actually switch the live and neutral round the other way. So we can control the phasing of the transformer in relation to the other transformers, which is very important when we combine transformers. So in other words, if we were to put one transformer on, we could push it upwards. If we wanted to bring another transformer in parallel on, we push another one in the same phase and a third transformer in parallel, all in the same phase. What we wouldn't do is put 3 transformers in parallel and put one of them anti-phase, because then they will basically be pushing against each other. One is in phase, one is out of phase. On the other hand, if we want to run 3 transformers in series, or 2 transformers in series rather, we might put 2 transformers in series like that. Now for 3 transformers in series, if we think about the microwave oven transformer and its design, it's okay to put 2 transformers in series, because normally you would end up floating one of the cores. So the upper transformer of the 2 in series, you'd float the core there, so it's not connected to ground, and that means that core is sitting at maximum load 2 kilovolts, or open circuit at 3 kilovolts. If you put a 3rd transformer in series on top with that core floated, you are talking about a floating core there of between 4 kilovolts at maximum load or 6 kilovolts open circuit. So in that scenario where the core is at, say, between 4 and 6 kilovolt in the top of the 3 transformers, you are starting to get a situation where the core to primary voltage is starting to get too high. So in other words, you can get breakdown or arc over between the floating core and the primary of that, which is sitting basically at the line potential. So in order to prevent that, if you want to run 3 microwave oven transformers in series safely, we take the first 2 transformers and we connect the cores together there, and then we run one as pushing downwards in voltage and one pushing up. So to do that, we would push that one in that phase and that one in that phase. So now essentially we are pushing the lower transformers pushing down to -2 kilovolts at maximum load, and the upper transformer is pushing to +2 kilovolts. The overall voltage differential at maximum load being 4 kilovolts for 2 transformers, or 6 kilovolts open circuit. If we want to add a 3rd transformer on top of that, we can. We add another transformer in series with the upper one, and we push that upwards. So now the maximum core potential to the primary, to the line supply, is now again, we're back to that 2 kilovolts on that upper core at maximum load, or 3 kilovolts. So the overall differential between the 3 is going to be 6 kilovolts at maximum load, or 9 kilovolts open circuit. And that's a way of putting 3 transformers, microwave oven transformers, in series without problems with arc over. Obviously we could have 4 in series and put the 4th one down to those 2 in that phase and those 2 in that phase. 3 is enough. From all the experiments, all I've done, a 5 kilowatt supply, plate supply, or other even high voltage supply. I mean, this goes further than just being a plate supply, although I call it the plate supply. This is a high voltage supply. Then 5 kilowatts at the kind of potentials that you get, I found more than adequate for driving whatever experiments that I'm doing. So that's how the phasing works. How hard the transformer's driving can be seen by how much these neon lights are illuminated, and that gives you the full control of the transformers. Okay, so when we get to let's come out, let's have a look at the other panel on here. So this now determines what happens at the output of the transformers. So in other words, to do with the output and anything you might have added onto it. So this is actually the current in the secondary. So however you got it connected, whether it's in parallel, whether it's in series, the lower leg of that passes through this meter, so we can see how much secondary current is flowing. This is an AC meter, because we're obviously running secondary is at 50 Hertz, coming out of the transformers. This is a UK line supply, and this goes from 0 to 2 amps. Very rare that you run it up to, you can put a 0 to 3 amp in there to cover its full range of output, but I rarely run it up anywhere near that point. So 0 to 2 amps is fine on the secondary circuit. There is then the output circuit, so in kilovolts. So this is a whole subsystem in there, which is basically this is basically a 1 milliamp DC current meter, which has basically got a resistor chain in front of it. So 1 mega ohm, 2 watt, 1 mega ohm resistors. If you put 20 of them in series, then 20 kilovolts is going to go down to 1 milliamp. If you put 10 of them, then you're going to have 10 kilovolts is going to go down to 1 milliamp, and so on and so forth. So I've got 3 ranges that are selected here: 5 kilovolts, 10 and 20. And then I use one of these Dymo machines to print out sticky labels, and then I can stick them on the screen. Essentially I can turn a 1 milliamp meter into any meter that I want with the divider. And also you can select the range, and these ranges are selected by using vacuum relays inside. So this comes through a rectifier. So in other words, even if you're just using the raw output with no bridge rectifier or no level shifter, then you can actually, this will give you the essentially the rectified output. So in other words, there's a half-wave rectifier with some high voltage smoothing capacitors, and then onto the divider chain, the resistor chain, which is then that resistor chain is selected by, as I said, high voltage vacuum relays to give you the range. 20 kilovolts full scale is basically all the relays off. 10 kilovolts switches in 10 of those 20 resistors, and 5 switches in 5 of those 20 resistors. The discharge unit, that's another subsystem inside. So there you have vacuum relays switching the final HT output through a high power resistor. That's a sequence of 5 resistors, wire wound, each 100 watts, making a total of 500 watts load. And that is, each of those is a 4K7. So you end up with about 23, I think it's about 23 kilo ohms at 500 watts. And for discharging a capacitor, you could discharge a capacitor from 15 kilovolts using that. There is 2 series vacuum relays on the input and 2 vacuum series relays on the output of those. So on the positive and negative sides. So nominally 12 kilovolts through the resistor chain, and that allows for safe discharging of a large capacitor bank. That can be switched here. Again, this is a lock switch, so it doesn't accidentally get put on. That can also be controlled from the remote control as well. You then have a bulb here, which on the inside is a normal incandescent bulb which illuminates when there's power applied to the transformers. So that will light basically at the final stage and before these switches. So basically it shows that there is power coming to the 3 transformer switches. If you have those transformer switches off, then obviously there is power available, but there's actually going to be no power on the transformers. As soon as you've got some of these switches on, if this is lit, then those transformers are going to be fed power. So it's a final safety or warning light that basically power, and it shines quite brightly as well when it comes up, and you can see the illumination from the side. So it's a good indication basically that the system is powered. You have some low voltage outputs here for auxiliary control, for example, a pulsing or a modulating or switching unit you might be using can be powered from those regions. So the final side is just I better zoom out first of all. Is the vent. So basically the airflow, this is where the airflow comes out. So it flows from the fans in across the transformers, across the rectifiers and other devices, across the capacitor bank for the level shifter, and then out through this side. And then if we look at finally the high voltage board, let's get that round. Let's just zoom in on that. Okay, so here these are the output. So let me just disconnect these for a minute. So the HT plus, that's the HT plus rail, that's the HT minus rail. They're all connected together. These are the outputs from the various subsystems. So you just have out plus and out minus. That's raw from the transformers. You have rectifier plus and minus. That's the output from the high voltage bridge rectifier. And you have doubler plus and doubler minus, which is the output from the level shifter. And to connect those to the high tension output, you just use jumpers. So let's get the red one on the red side. So that's the rectifier. So the transformers, if they are internally connected to the high voltage bridge rectifier, then this output now comes to the HT output. If I were to move those there, I can get the raw output. If I move them out to the doubler, then it will be the output of the doubler or level shifter. These are just high voltage terminals connections. They allow capacitors to be put in series. So I can take a capacitor out from here, the other terminal comes back to here, out to the other capacitor, back, and so on and so forth. So it basically allows me, easily gives me a terminal to connect high voltage capacitors together. There's also two outputs here for the transformer earth, so that's the same as this one here. So this high current one, which basically will take out to say a Tesla coil, the bottom end of a Tesla coil or other units which we're driving, and there's also in a 4mm quick push fit setting as well. They're connected together, so effectively they are the same, and that's also the same as transformer earth here. So all of these with this jumper in are connected to the line earth. If I disconnect that, transformer earth is now floating from the line earth. Okay, so that's the four panels and how they're all laid out. Let's have a look at how we adjust the inside. So I'm going to use it from this side and zoom out. Okay, so this panel is easily removable, like so. And this gives us access to the various internal boards. So we can see in the background there are 3 microwave oven transformers. This is the patch board or connector board, which will allow us to determine how each of those transformers, 1, 2 and 3, are connected together by jumpers. Then we have a board here which is for the monitoring circuit, so it's got our 20 divider chain resistors. We've got the level shifter here this unit, and then we have the discharge unit here. So what I'm going to do is I'm going to take out. This is designed in a modular way. So in other words, this section, which consists of the level shifter and the monitoring circuit, come out as one board, and the transformers, the bridge rectifier and the patch board also come out as one unit, and also so does the high voltage discharge unit. They are all removable units from this, and then that allows us to see. I'll unscrew this board, this panel, open it up, and then we basically have a look at how the whole thing is constructed internally. So I'm just going to take those out, and then we can work on, clear some space on the bench, and then I'll have a look in detail at how it's all wired up internally and how it's designed. Okay, so now I've removed the two main boards from the centre of the plate supply, put those out on the bench. Just have a look at those. That's the transformer board, rectifier board on the right, and the level shifter and the divider chain for the monitoring. So now we've got those out, we can take a detailed look at how this thing is assembled, how all the parts go together. So just on the inside of the plate supply, here we have the 12 kilovolt, nominally 12 kilovolt discharge unit. So there's 500 watt 4K7 power resistors there in series at the bottom level here. At the top here you've got 4 vacuum relays. They're nominally 3 kilovolts at 10 amps, but I found them to be good for quite a bit more than that, so particularly when it's just for a brief discharge. So 2 in series on the positive HT side, and 2 in series on the negative HT side. These are laced up and powered by the 24 volt module here on the low tension side. So just moving the camera in and just looking at the power control side, so that's everything down this side of the plate supply. As I said before, there's a 24 volt module that runs off of the 15 volts and gives 24 volt out to DC to DC converter. There is the 3-pole switch here to switch the external power meter. Obviously power coming in from the rear panel. Each of these panels is designed so they can fold out for easy work on them. So for example, this panel here would fold this way. This panel folds out this way, and the front panels fold out downwards. So low tension switching here, along with the fuse and the indicators at the top. There's a 32 amp double pole MCB on this side as well. That's obviously for the transformer line supply. The internal SCR, this is a nominally, well, it's called a 10 kilowatt SCR. I think it's really good for about 4 to 5 kilowatts continuous. That's got its own fan inside. There is the dual cooling fans, which line up in between the transformers, so they pass air across the transformers and across all the other components and vent on the left hand side. Then there's the line source select double pole switch, which either switches on the panel to SCR or to an external line supply source, which might be, for example, a variac or some other kind of power control. Now just moving, if I move this round slightly so we can see what's on the front panel. Okay, so here we have the changeover switches for the phasing of the transformers. So they're fairly tightly wired together, along with the battery operated power meter, various meters, a current sense for the power meter, and the various SCR and switching controls, output for the remote, and on this side the various meters and the high tension meter, the secondary for the transformers, and the various low tension outputs, and they go together, and also the bulb for the to show that the transformers are being passed power. So the supply relatively simply laid out. Power comes in, let me just put it at the back. The design is arranged to be simple, so power comes in at this side and progresses down this way into the front panel and then into the transformer module. That makes the wiring more simple and also leads to a natural, logical way in which the thing is designed and assembled, which also makes it easier to repair and work on should there be a problem. Wiring that has to be passed, interconnecting wiring, is in this conduit here. So for examples of that, here we've got the 15 volt low tension power supply. It's a 3 amp 15 volt switch mode power supply that feeds power both in this direction to the front panel, and also feeds power down to the 24 volt module. That was the place where I could fit the 24 volt module, and the 24 volt module is primarily used for the switching of the vacuum relays. You can switch those to the 15 volt, but it generally is not necessarily reliable on all of them. So normally they take up to 27 volts, so 24 volts is a good reliable switching for the vacuum relays. Other wiring that goes in here, for example, when if you switch to external power meter, you've got a return line going down here, out and into the external power meter switch, and obviously there's a line coming back which is feeding the neutral into the front panel. Otherwise, I think everything's relatively straightforward. They're simple components, easily available. Probably the most exotic components here are the vacuum relays, but otherwise this plate supply is intended to be very flexible, easy to use, easy to repair, yet you can use it in many different ways. Okay, so let me reposition the camera and then we're going to have a look at the sub-assemblies. So we're looking now at the transformer. That's one of the three main sub-assemblies that go into the plate supply. One is the transformer, the other is a level shifter, the other is a discharge unit. This is the transformer unit. It has three industrial microwave oven transformers on here. Obviously they're mounted on a nylon base, so one of these transformers, up to one of these transformers, would have its core floated in a series arrangement, and in that scenario you don't want it to be on a conducting base, because the core is going to be sitting at a potential of the output of the lower one. So let's say we're using this as the lower transformer, we've got these two in series, then open circuit, maximum input, this is going to be sitting at about 3 kilovolts, which means when it's connected to series here, this core in itself is connected to that 3 kilovolt output, and then the output of the top end of the secondary here is going to be at 6 kilovolts open circuit, but full load 4 kilovolts. We wouldn't ordinarily connect more than 2 transformers in series on top of each other, because you have to consider the core voltage to the primary. I mean, although these are not relative to earth because they're mounted on a nylon plastic base, it does affect the potential difference between the primary, which is essentially at the line supply, and what you don't want to do. If you take it too high, you obviously have a risk of breakdown between the core and the windings of the primary. Putting 2 in series above is too much. I've found that it will cause 2. You can get a flashover because you would be raising the core open circuit of the 3rd transformer up to 6 kilovolts and 9 kilovolts at the output end of the secondary. If you want to connect all 3 in series, the trick is to join the 2 cores here together. This secondary, the lowest secondary, pushes downwards to minus 3 kilovolts. This one pushes up to 3 kilovolts. This core is floated at the end here, so it's at 3 kilovolts, and the output of the secondary here is at 6 kilovolts. So the entire potential difference across the 3 transformers is the 9 kilovolts, but you never getting the primary too far. The primary to core is never getting it close to a flashover point. Anyway, that's a more advanced way of running it. I just wanted to talk about how you could actually connect these in series and why we're actually mounted on nylon. I mean, I use nylon a lot for high voltage. It's extremely good and gives an excellent isolation. It's quite strong, it's relatively easy to machine, and it forms a good base for this kind of high voltage work. So these are, going back to the transformers themselves, these are RTRN A741s, normally 1.8 kVA industrial microwave oven transformers. They have to have the shims removed. Microwave oven transformers are usually designed to work in a very specific impedance range into the magnetron, and in order to provide the correct current limiting and hence reduce the power output to exactly what is the requirement of the magnetron, shims, you put shims, steel laminated shims, in between the primary and the secondary coil, and that limits the coupling and the magnetic field between primary and the secondary. You introduce a loss there, magnetic loss, with those shims, and that produces, when coupled with the impedance of the magnetron, then even when you apply maximum line supply to the primary, you are essentially getting the right power output from the secondary, which is, in this case, of course, limiting. We want to make full use of the power capabilities of the transformer right up to its top end performance, and to do that we need to knock out the shims. That does mean that you need power control. With a microwave oven transformer, you have got essentially a core here which is welded together. They're usually welded together to hold all the laminations together, and that essentially shorts out the core. So if you were to just put a line supply sinusoidal on this, or not current limit it in some way, then you very quickly run into core saturation. It draws enormous amounts of current from the supply, and it will get extremely hot. So we need to We need to limit the current with this. There are several ways of doing that, and one can use, obviously a simple way is to use a choke. A very common way is to use, in effect, another microwave oven transformer in series with the primary, shorted on its secondary, and that actually obviously produces a choking effect, reduces the maximum current. I tend to prefer to use power control, so that, for example, is why I use the SCR internally, because that is essentially you are controlling the on time in the cycle, and you can do that quite accurately, and especially when you are using the output, which is rectified and then goes through a high voltage capacitor. Then just to stabilize, you end up with a solid DC output, but then the transformer never goes into saturation or overload, so you can control the output quite straightforwardly there, as I will demonstrate later in the video. The phasing of these can also be switched. So from the front panel, as I've already shown, the switches can be adjusted to be off. So all transformers can be off or all on, and the phase of the live and the neutral to the primary can be switched. So, for example, if they're running in series in the way that I said before, with 2 up, 1 down, you have 2 in phase, 1 anti-phase. If you're running all 3 in parallel, then you'll have you run them all in the same phase, and that in a way gives you a very configurable way of running these transformers, and that can be combined either with just a raw output. So you just take the output directly off of this jumper board directly to the back panel in the power supply, or you can take it through, you can switch it through the bridge rectifier, or you can put it through the level shifter, which gives a very wide range of output powers, or output voltage and currents, different waveform shapes, all the way from just pure sinusoidal, all the way up to rectified and smooth DC in a tank circuit, like for example when we're using it as a plate supply, high power plate supply. So those are the transformers. They are all mounted down with nylon bolts. So again, we are cognizant of how everything is mounted together in terms of the high voltage isolation. Remember, we might be running this with a total potential across those transformers open circuit at 9 kilovolts. 9 kilovolts is a hefty. It's about, in air, about 30 kilovolts per centimetre. So we are talking about, at 9 kilovolts, we're talking about 3 or so millimetres that the potential could jump, and we are talking about, with microwave oven transformers, we are talking about very high levels of current. So these transformers can provide a very a heck of a punch in effect, and in that respect, how we lay it out, how we wire it is very important. You can see that all the wiring that comes out of the switchboard that goes to the jumper panel, that goes to the back panel, and the various interconnects between the various boards, they're all done with 20 kilovolt AWG16, 20 kilovolt silicone wire. And I've never really had a problem with this wire. It's very good at this kind of level, more than adequate for the type of currents that one's putting out on the secondary side. Typically, maximum current output this will ever reach with 3 in parallel is somewhere up at around 2 to 2.5 amps. So the high tension 20 kilovolt AWG16 alpha wire I actually use here is really good to make sure that everything remains isolated and is more than sufficient for the output current requirements of this power supply. So the jumper board itself, each transformer comes to its positive and negative output. Here, one side, the negative is obviously connected to the core, and the positive side is at the top end of the secondary. So you've got 3 outputs and 3 transformers, and then there's a range of different ways in which you can connect these together. In fact, we'll go through this now actually, since I'm on this point. So first of all, there is a common earth line that doesn't necessarily connect to the line supply earth. You can disconnect that, so I distinguish them as a transformer earth and a line supply earth. This is the transformer earth. It also connects to outputs on the back panel, which are transformer earth, and there is a jumper at the other end at the line input, where you can connect transformer earth and line supply earth together if you need to. In some scenarios you do, in others that you don't. For example, if you were running these 3 in series, where this end is at minus 3 kilovolts and this end is at plus 6 kilovolts, with all 3 in series, you're not going to be connecting the bottom end down to the transformer earth, this end, because in effect you're running at minus 3 kilovolts for the bottom end. Then that is an example where you would not be connecting, for example, the transformer earth to the line supply earth. So this forms a common rail, the blue. So if I wanted to connect all 3 of these transformers in parallel, I would simply just connect T1 to E1, T2 to E2, T3 to E3. I'll go through this matrix of connections on the right up so you can see how it all works. So that would put them all in parallel. In this case, this board is set up just for using 1 transformer. The other 2, these aren't doing anything at all. The black lines on here shows where there are connections. So these jumpers are just stored for these 2 transformers. So the outputs, if we look at one transformer here, the negative side of the output of the transformer, which is essentially the core here, which is held down to transformer earth and can also be connected from transformer earth to line earth. So this is actually an earthed core in this configuration. That actually, the negative side is where we've got the secondary current, so it's marked A secondary, ASEC on the front panel, and these 2 green terminals are for that meter. So, and it incorporates a fuse as well. So in effect, the negative terminal comes down here, is connected into this green terminal, goes through the fuse, and then the output of that fuse goes down to one side of the current meter. The other side of the current meter is, or the return is from here back to, and here we've got it plugged into the negative end of the rectifier. I might have that, for example, plugged into the negative end of the raw output. Or I might change this configuration like this. So now the negative end basically is the negative end of the level shifter or the doubler. Let's put it back the way it was. It's the way I was using it. Here, okay, so we're going through the secondary current meter and then to the negative end of the rectifier. The positive output of this meter is, of this transformer, is coming across this link onto the positive output rail. That's this connection here. They are all connected together. Nothing else is connected into this rail, just this one. That obviously comes down here through the fuse out to another, the green terminal, that's a fuse connected terminal, and I've got a jumper here which takes us into the positive end of the rectifier. So in other words, through these jumpers I have a single transformer with a negative end connected through a fuse and a current meter, and the positive end of the transformer connected to the fuse and into the rectifier, and a negative end also into the rectifier. So in other words, that's using the bridge rectifier in this scenario. As I said, I could have reconfigured this to run in a different way. So for example, if I wanted to use the first two transformers, and I wanted to use them in series, then I'm going to remove this. Let's put it back in its, that's just a storage position because those two are connected. Then I'm going to take this one, the negative end, connect it down to the positive output of the lower transformer, and I'm going to take this jumper and I'm going to jump that out to the output. Now when on the front panel I set two transformers in the same phase, these two, so transformer 1 and transformer 2, when I set them in the same phase position with the three switches, the first two will be either set upwards or they'll set downwards, which turns them both on in the same phase. Then I've essentially now got two transformers in series going to the bridge rectifier. So that's a two series situation. Now, if I wanted to do a 3 series, then I've got to rearrange this quite considerably, because like I said, this would be a negative end, so minus 3 kilovolts. This will be plus 3 kilovolts. This will take it up to plus 6 kilovolts. So in a 3 series situation, I'm going to first of all connect the two cores down here. So let me borrow one of the other jumpers here. For example, that's going to go down to there. So the two cores are now connected together. I'm going to use the let's take that one away. I'm going to be using the positive output from this one through the fuse back out into the rectifier. Okay, so that's now providing at this point relative, it's going to produce minus 3 kilovolts. I'll put the switch at the front down on the front panel for T1 to turn that one on and say that the phase is set in a particular direction. Now I'm going to jump series. So we're not going to connect the connection together there. Actually, I prefer to keep the colour codings right because it also helps me visualise how the circuit works. Okay, so these transformers are already connected, so now we're going to put these two in series. So the output of this one comes up to here. It's going to go series onto there, like so, and then the output of this transformer, top end, will feed the final output rail. Now we've got all three of these in series with these two cores connected together and through E1 and E2. This end comes down through the correct selection of the phasing to minus 3 kilovolts. This one with the opposite phasing connection will come up to plus 3 kilovolts. This one with the same phasing, primary phasing as this one, will bring it up to plus 6 kilovolts. That comes out of this output line through here and into the rectifier. So this end is at minus 3 kilovolts, this end is at plus 6 kilovolts, and we do not have the line supply, the transformer earth supply connected to the line supply. So that's another way in which we can configure all of this. The empty ones, if I can, I try to put them back. Okay, so that I think gives a clear view of how this panel works. And you, as I showed before, you correspond by connecting the correct outputs at the back of the output board on the back. So each of the raw output, rectified output, and the level shifter or doubler output come out to terminals at the back, and you can connect which of those goes to high tension plus and which of those goes to high tension minus. So in effect, quickly and safely we can configure this power supply to run in lots of different modes, and I'll put all the options and ways and what it can produce in a matrix in the write-up. That was one of the reasons I built it this way, because I wanted to run different experiments, different types of tubes. It takes a lot of time and effort to build and test the power supply like this, and really I only really wanted to do it once and then have a supply that I could use really for all my experiments, including experiments with thyrotrons, medium power thyrotrons for pulse work, and those kinds of experiments. So I can get the high tension, very high tension, doubled with all three in series like this connected to the doubler. Then open circuit, you'll push up to 18 kilovolts. Under load, 15 kilovolts at 200 milliamps. 12 kilovolts at about 400 milliamps, which is a heck of a punch. That's a very, very high tension supply. And like I said, it powers all of the kind of experiments that I do on a regular basis. So, input down here, these are the transformer primary inputs that come from the front panel, and if I rotate it round now, we can see the bridge rectifier underneath. I'll just find something to prop that up with so one gets a better view of what's underneath. Let me just prop that up slightly. Okay. Alright, so that gives a view of the bridge rectifier. So the bridge rectifier is 4 banks of 3 high voltage diodes in parallel. So it's a full bridge. Let me just check if I can see what type these are. These are PRH VP 2 amp 20 kilovolts. So each diode is a 20 kilovolt 2 amp nominally. So 3 in parallel give 6 amp capability to each arm of the bridge, and 20 kilovolts. So total of 40 kilovolts. And there's 2 arms in each direction. So that's 40 kilovolts, 6 amps bridge rectifier, which is more than adequate. I like to double up on double or triple everything, and then you don't get burnouts. You don't get mostly you don't get burnouts or blowing semiconductors. This semiconductor bank is protected by the 2 fuses on the top here. That was primarily why I put them in. Originally I didn't have them, and I did end up it going short circuit at the output when I was doing a certain type of test, which put too much current in the bridge. It pulled too much current. Obviously these transformers are able to push enormous amounts of current in a short circuit situation without the shunts, with the shunts removed, and it basically just took out all 12 of the semiconductors. So I put the fuses in. That stops that condition quite adequately. I would run those with a 2 amp quick blow is enough. You can run it continuously between 2 and 3, and it's still going to be okay. But you know, once you get up a little bit higher than that, the fuses blow quite quickly, which is good. It protects. Since each arm is 6 amps rated, it's adequate to protect and the semiconductors there, and not had a problem with it since. So again, that's all mounted down on nylon screws. It's all wired up underneath using the same 20 kilovolt silicone wire. I'll see whether I can just rotate it up onto its back with another block, the block down there to protect the transformer windings. And it may be possible, let me check on the camera. Oh no, that doesn't help at all. Well, I have some pictures of the other side of that, so I will show those on the right up of the page so one can see how it's connected. And that really is the transformer board. Layout is careful, taking into account the type of voltages and currents involved, making sure that circuits are protected with fuses and with the adequate type of wiring that you need for this kind of high voltage supply. But otherwise, it's actually very straightforward. It's just a set of transformers with some rectifiers and a patch board wired up in a way which makes it possible to configure it in all types of different configurations. Okay, all right, so that's the transformer board. What I'm going to do now is have a look at the doubler board. I'll probably just swap them over to get them good into the camera view. Let me just do that. Okay, so I've swapped over the boards. This is the level shifter board now, sometimes incorrectly called doubler, but it's sometimes I use it interchangeably. It's easy to make that mistake, but it is actually technically a level shifter. So the level shifter consists of a series capacitor. So this is a capacitor bank. Each one of these is a 1.05 microfarad, 2100 volts, 2100 volts AC. It's a microwave oven capacitor. They're used in microwave ovens to do the level shifting for the magnetron, and also to tune the magnetron to the transformer output. That's normally done by a slight adjustment of the value, so anywhere from about 0.9 microfarads up to 1.2 microfarads. So I'm using this as, I want to use this as a level shifter that will basically take at maximum 3 microwave oven transformers in series and level shift that safely. So those microwave oven transformers are nominally each 2100 volts out, so one transformer goes together with one capacitor. So if I've got 3 in series, where we're talking 6300 volts fully loaded, then we're going to have 3. We've got to have 3 in series. So we distribute that potential across the 3, and we keep each of the capacitors within its normal operating range. So we've got a series bank of 3 capacitors here. So fully loaded, that's 6300 volt at a third of a microfarad. We've got 3 in series. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've got 11 parallel rows here. They're all connected up this way and that way. Again, using silicone wire. Because they're just interconnects here, I'm not using the 20 kilovolt wire. The connections are short and they just go from capacitor to capacitor. So I'm using the normal AWG16 silicone wire that I use to connect up high voltage parts of the experiment. So in total, that produces a 3.9 microfarad, or roughly 3.9 microfarad capacitor at 6.3 kilovolts fully loaded and 9 kilovolts open circuit. So that is fed as a level shifter has a diode. Let me just make sure we can see that. Yep. I might prop that up again just so that we can see what's going on underneath. Okay, so there we have again 2 banks of 3 high voltage diodes in parallel. So this is a 6 amp, again they are PRHV P2 amp, 20 kilovolts. These banks are in series and come from the negative end up to the positive end, up to the positive end of the capacitor. The negative end of the or the incoming end of the capacitor comes off of, not one of those. Where does it come? It comes off of the that goes to the positive end. The wire is on the transformer board. So the transformer board negative end of the level shifter will come through here and go onto this terminal here. So you've got a series capacitor. The level shifter obviously works by shifting the whole waveform, output waveform, up by the nominal voltage of the transformers. So in effect we're taking a positive and negative going sine wave, and we are shifting that up to the centre point so that the bottom end of the sine basically becomes 0 volts. So that's why it's called a level shifter. We are basically shifting the whole waveform upwards. So that gives us a top envelope with 3 transformers together. That's going to, at full power, it's going to reach 12 kilovolts. Open circuit is going to be 18 kilovolts. When you run a thyratron with this, you're running somewhere around about 14-15 kilovolts, and it provides an adequate plate supply for a medium power thyratron, which is just what you want for experiments, so impulse experiments, and also displacement of electric power experiments, as I write about on my website. They all work very well with thyratrons, as we're going to see. So again, it's a very simple circuit. It's overall 40 kilovolt, 6 amp diode, which works with the capacitor bank, and that does the level shifting for the transformers. Now, what we also have is we have another unit bolted on top of this. This is the metering, so the high voltage metering. So this is what takes output off of the high tension at the back and feeds it down to the high voltage meter, or the meter that shows the tension at the back here. And this is basically designed so that it can measure the raw output as well, unrectified. So we have a half-wave rectifier in here with 2, again, high voltage diodes in series. That incoming, again, we've got a fused down here, just in case this would be another, because this is connected directly to the output. If there were any arc over in any of these components, either down to the low voltage, to earth, or to another part of the circuit, then we could end up with a tank capacitor charged up on the output. We could end up with enormous discharge currents through these semiconductors, which I have had that situation before. I didn't used to have fuses here originally, and I did end up in that condition, and one of these semiconductors just blasted to pieces, which is both very loud and not very fun. And these are Bakelite cases, and they tend to throw Bakelite pieces all over the place. So putting a fuse both in the incoming and in the outgoing, because you don't know where the arc over is going to occur, So it's important to have both ends, both directions of the, if you're running at negative HT or positive HT, where that arcs down to is going to affect which one of those is going to blow first. So having them both fused is important. So it comes through the half wave rectifier onto a capacitor bank, an accumulated capacitor bank here. That basically smooths out the ripple so that we can actually get a reasonable reading on the front if we were in raw mode. So those are 10 nanofarad each, 20 kilovolts, 10 nanofarad capacitor. So each two in series is 5 nanofarad in parallel. So basically all four together produce a 10 nanofarad 40 kilovolt tank capacitor for the measurement side. That then is fed down a resistor. So ultimately we are trying to feed it down to a 1 milliamp meter, and then we have various switched feeds, high voltage feeds off of here. So to get our 5 kilovolt, 10 kilovolt and 20 kilovolt range, with both of those off, we have got 20 resistors in a loop. So it comes down through the meter, back through these. The supply is supplied here by the half wave rectifier. So that will give us 20 kilovolts will go down to 1 milliamp. There's 20 1 mega ohm 2 watt resistors in series. For 5 kilovolts, this comes on and it takes a tap. It takes a tap out of the second one here with 3 return. That gives us 5 1 mega ohm resistors. So we take 5 mega ohm. So we take 5 kilovolts down to 1 milliamp. And this one here, this vacuum relay, is off the taps 10 resistors. So then gives us 10 kilovolts with 10 resistors down to 1 milliamp again. So the switch at the front between 5, 10 and 20 kilovolts actually controls the switching, the low voltage side switching of these relays, where both relays off, so with no power, both relays off, the meter would be in 20 kilovolt as the default, as default mode. And that works reliably and safely. Now, you might say, well, how can you put a 20 kilovolt onto potentially, or somewhere up about 15 onto a 3 kilovolt relay? Remember that we have considerable resistance here. So the terminals can't arc over because the current is very, very restricted. That's why you can use these kind of relays in this kind of situation to basically bridge from a different point in the divider to the output. And that works very effectively in being able to safely switch the high voltage in different ranges on the front panel. Now, of course, the front panel that's good because you have a plastic shafted rotary switch on the front, and that is only switching the 24 volts to one relay or the other. So you don't get any of the high tension from this end anywhere near the front panel, which is good when you, of course, for safety when you're doing and when you're working with various experiments. So that really, that's another. I mean, the construction is quite complicated in that one needs to do it carefully and to make sure how you lay it out. There's a guard here, a guard sheet between this monitor circuit and the high voltage capacitors. I did have a problem where before, like I told you, that one of the semiconductors had too much current and exploded, and it actually damaged two of the capacitors here. So I subsequently put a guard in nylon sheet guard here to prevent any damage should we have another semiconductor failure. But that's all handled by these fuses now. So provided that your tank capacitors got bleeder resistors on them, then even if there were a problem in the circuit, one or both of those fuses blow and protects the various components in the circuit against damage. Okay, so those are the two main sub-assemblies, and that really does cover the internal boards that are used in this system. They can be easily put in and out. They just slide in and the connections reconnect to either the front or the back. So that's the inside. It's a breakdown of how it's assembled and the kind of design considerations that I went through when actually working out how to build this kind of supply, versatile and in a safe way. Great. And I just need to connect the power up. Okay, and then we can just turn the various units on. So, turn on the coil unit. I'm going to wind up the filament current slowly up to 20 amps, and obviously it's cold, so I'm not going to just wind it fully up. I'm going to let it warm up slowly. It's a large tube. If I just had the variac set where it would be nominally, and turned it on, there'd be a very large inrush current. We don't really want to do that. We reduce the lifetime of the filament. Okay, turn that up. 20, it falls away. We're winding it up until the voltage reaches nominally 12.6 or 12.5 is really as accurate as we can measure on the meters that we're using. Back up to 20 amps again. Now to 7.5 volts. $10 volts, just over 20 amps. And finally up to 12.5. Between 23 and 24 amps being consumed by the heater, and we're just going to let that warm up for a bit. In the meantime, I'll just turn this on, so the low tension's on, the high voltage is on, the power screen is also on, that's a complete power unit in one. It shows voltage, current and real power factor all together, particularly useful. Okay, I just have a final check, make sure everything's connected correctly. Using the rectifier. The rectifier is set here. Blocking capacitors connected and the high tension is connected as well. We've got two transformers selected. We set it to SCR, so SCR input, and we are basically using a remote control, so we don't have to get close to the system when we're running it. And I'm going to bring the lights down. Okay, so there's the lights down. You can see everything's up. And we'll wind up slowly. And we can see the image first of all. It's low tension. Just check it's coming out on the image. That's 1.8 kilowatts. Let's just see if we can. So we're running at 1.8 kilowatts CW, and we can see the structure and nature of the discharge. Okay, so that shows how it all operates together. we're consuming about 13 amps, wheel 17.2, obviously its apparent power is different, power factor 0.47, it's CW. Okay, give the system a little bit of a chance to rest, and I'm going to move the, now I've seen everything working together, I'm going to move the camera into close proximity, or closer proximity to the discharge, so we can actually look at the discharge itself. Okay, so I've given the system a little bit of a rest and a chance for mainly the primary to cool down. Transformers and the power supply are barely even warm. So we're going to wind up slowly again, looking at the structure and geometry of this fractal fern discharge. We're just breaking out, just under 200 watts. 250. Not really seeing much of the fern structure yet. Got to go up, got to push it harder. 300. Okay, now we start to see some of that, and we also notice a change in the sound. Before it was harsher, now it's become more steady. Just hold it there, about 360 watts, right at the beginning. Up in power, start to see more bifurcation, start to see the proper development of those primary tendrils. We start to see the secondary and even tertiary tendrils in some cases. Self-similar like structure, fractal type structure. Orthogonal nature of each of the secondary and tertiary. Now we're up to 500 watts. Fully developed. That whole structure is about 25 centimeters high, sometimes 20 to 30 centimeters high from the tip upwards. 1.9 kilowatts now. Very well developed, very strong. All in CW. It's about a kilowatt. Fine detail, very fine nature will come out on the photographs. The tiny fronds, displacement like fronds that go into the tendrils. Very good, nice and stable. GU5B has no problem pushing this. Now there's the power supply, we're running at 1.85 kilowatts. Back down and off.